Imagine a world without electric motors. No fans to cool you down on a hot day, no washing machines to clean your clothes, no cars quietly gliding down the road on battery power. Electric motors are everywhere, powering our modern lives in ways we often take for granted. But how do they actually work? What makes a simple coil of wire and a few magnets spin with enough force to drive machines big and small? It all comes down to the incredible power of electromagnetism. Over 200 years ago, scientists made a fascinating discovery. When electricity flows through a wire, it creates a magnetic field around it. One of the first to experiment with this idea was Michael Faraday, who showed that electricity and magnetism are deeply connected. His work paved the way for electric motors, which use this principle to generate motion. To see this in action, let's do a quick experiment. If you take a simple coil of wire, place it between the poles of a magnet, and connect it to a battery, something amazing happens. The coil starts spinning. That's because the magnetic field from the current in the wire interacts with the field of the magnet, creating a force that pushes the wire in a specific direction. This force, called the Lorentz force, is what makes an electric motor move. A real electric motor is built with a few key parts: a rotor, which is the spinning part, a stator, which holds everything in place, and a power source that supplies electricity. The rotor contains wire coils that become electromagnets when current flows through them. Surrounding the rotor are strong permanent magnets or electromagnets inside the stator. As electricity flows, the rotor's magnetic field interacts with the stator's field, creating attraction and repulsion forces that keep the rotor spinning. But there's a challenge. Once the coil rotates halfway, the magnetic forces would normally stop it from continuing. This is where something called a commutator comes in. In DC motors, the commutator is a clever switch that reverses the current at just the right moment, flipping the magnetic field so that the rotor keeps spinning. In AC motors, this switching happens naturally as the power supply changes direction many times per second, eliminating the need for a commutator. The power of an electric motor depends on several factors, such as the number of wire coils, the strength of the magnets, and the amount of electricity flowing through the system. Industrial motors, like those used in trains and elevators, use powerful electromagnets and high voltage to generate massive amounts of force, while tiny motors in electric toothbrushes or toys work with small currents and lightweight parts. One of the most fascinating things about electric motors is their efficiency. Unlike combustion engines, which waste a lot of energy as heat, electric motors convert most of their energy directly into motion. This makes them ideal for electric cars, which use powerful motors to turn their wheels. The same principles that power a small desk fan are also driving the future of transportation. In fact, some of the world's most powerful electric motors are used in submarines, bullet trains, and even roller coasters, delivering incredible speed and strength. Electric motors have been around for more than a century, but they continue to evolve. Scientists and engineers are constantly working on making them smaller, stronger, and more efficient. But here's something to think about. If electric motors are so efficient, why aren't they used in every form of transportation yet? Could we one day see airplanes, cargo ships, or even space rockets powered entirely by electric motors? The next time you turn on a fan, open your fridge, or start your car, take a moment to appreciate the unseen force of electromagnetism that's working behind the scenes to keep your world moving.
Got a question about how something really works? Drop it in the comments and we might cover your topic in our next video.